Right, so hi, I'm Simon. I'm an intensive care consultant from Leicester Royal Infirmary. Everyone's here. So based on feedback from my last riveting and exciting talk with statistics, um, people asked maybe if I could talk about how to read a paper. I assume most people know how to read, so we're going to just go through about the actual way in which you approach a scientific paper and how I do it. Right, so with no further ado. So first of all, why do you read articles? Well, some people take CPD seriously and read professionally. Some people do it because they've been on a ward round and they've found something interesting and they're curious, a bit like my dog here, who never leaves me alone. And the other reason, the most popular reason for why people read an article is because they're told to. Usually for something like Journal Club, or because some consultant wants you to explain something. And the other reason, which Dr. Charlton can recognise at the moment, and I certainly have, is when you're writing up your thesis, you need to read lots and lots of papers. And not really only just for the, not just for the outcome of the paper, but actually for reading things like methods and getting an idea of how other people have done similar experiments to you. So there are a few reasons to read, but by far and away, I think the most common reason people read an article is because they're told to. So the problem with research is that there's too much, and too much of variable quality. So one of the estimates is that there are 2 new papers published every minute of every year, and I think this quote from this tweet from someone I don't know, but I downloaded it anyway, is that essentially doing research is spending a huge amount of time reading lots of papers only to write a tiny bit in a sentence. So so when you do read a paper, I think you do have to be relatively quick and concise about it. Otherwise, you get very stuck down stuck down with all the articles that are available. So what I thought break this down to is based on something from the Centre of Evidence-Based Medicine in Oxford, which is what you do when you get a paper. And I think these 4 questions are crucial, because if you can't answer yes to these 4 questions, then you just put the paper back in the bin. So the first one is, does this study address a clearly focused question? And I think that's really important. The study has to be clear what the question is and what hypothesis they're trying to demonstrate. And when I go through this talk, I'll use these headings to highlight the points I'm trying to make. Did the study use valid methods? So, are they statistics and research methods that are commonly used and valid? And are the results important, or what I call the so what question? If you beat presentations of papers and presentations of studies, there's often a huge amount of talking and graphs and pictures, and at the end of it, I always find myself saying, so what? And it's all very interesting, but what have you actually demonstrated? Is this actually of any use to anyone? And the final bit is the bit that is really why Journal Club exists. I'll skip to, I can't go backwards. Anyway, the reason Journal Club exists is really saying, is the information presented in this paper relevant to my practice? So to answer question 1, I think when you read a paper, they're the 4 questions you should have in mind, and they're the 4 questions you should be able to answer by the end of the paper. And I think when you're presenting them, it's useful to divide them into those sections. So first of all, what is the question? So usually they write it in the title. Usually there's some sort of very long-winded title, which tells you roughly what they're trying to answer. Though increasingly people now like making up weird acronyms out of strange letters from the words, which doesn't always really tell you what's going on. So if the title doesn't give you the answer, the abstract may, so the abstract can be quite confusing. But the introduction, and the nice thing about a good introduction is that it tells you all the background to the study you're doing. So it'll go through all the other papers, all the other research that's been done, and should, if it's well written, highlight the areas of controversy and why the paper that you're reading now is so important and useful to science. And I think sometimes it can be quite useful to see if you can generate in your head the null hypothesis. So I don't know if people remember my wonderfully interesting talk last time, but I talked quite a lot about null hypotheses. But essentially, what this is the kind of negative hypothesis. It's what you're trying to disprove. So the null hypothesis would be, for example, like there is, let's say you're looking at drugs for hypertension, and the paper is titled labetalol effectively reduces hypertension in obstetric patients. Well, the null hypothesis would be labetalol does not effectively reduce blood pressure in the obstetric population. And if you can't, in your head, based on the introduction, based on the title, generate a null hypothesis, it's quite hard to see then how they've been able to prove anything. So it's a way of focusing yourself, your mind, on what is the question that's being looked at. So that's the first bit. The second bit is the bit that is the methods, really. It's about, did the study use valid methods to address this question? And I find this bit really very confusing in papers, because there are, like medicine, there's lots of jargon in statistics and studies, only about a third of which I ever really understand what it is. So you'll get things like propensity match scoring, cohort, longitudinal, I can't remember what MAM stands for now, IPD, meta-analysis, you get a whole bunch of phrases thrown at you, and it can be quite hard to work out what it is the authors did. So how do I get around this? What I do is, first of all, recognize what jargon they use doesn't really matter very much. It doesn't matter what the study is. What a good and well-written paper will do is explain clearly what the authors actually did. So it should go through where they got the patients from. It should go through how they randomized patients, how they identified them, what databases they drew the information from, and over what time period, for example. And if the paper can't clearly explain what the authors did, then again, it's probably not worth persisting with. If it is just using lots of confusing language, and I always find it slightly ironic that scientific papers are designed to communicate knowledge, but more often than not, they're almost completely indecipherable. But if you are in doubt, another way of doing it is to draw it out. So draw out the methods. What I mean by that is that you can write down and draw the groups. So you can have one group on one side, one group on another side, and you can see then what it is they were doing. And if doing that and it's still confusing, then I think it makes it quite hard to, I would probably say this isn't a well-written paper. It may be accurate, but it isn't well written. And I also think a really important thing to do, something doctors do a lot, I find, and I do it myself anyway, is try not to criticize. Try not to criticize the paper until you've got to the end. So what people say, they'll read the methods and they'll say, this is a study of 20 people, and instantly you say, oh no, it's not relevant. Or the P was 0.06. No, not relevant. It's rubbish. Don't criticize the paper until the end, or until you actually get to the proper critique. And part of that is that actually the study can be interesting and it can be valid and it can be useful, even if p-values are a bit big, even if it's small, even if it's retrospective. Everyone seems to decide anything retrospective must never be published. Well, that's clearly nonsense. Where most of our scoring systems come from. So, don't use these standard criticisms that you'll develop until you get to the end, until you've read the paper. And I'm going to go on a lot about this today. It's not all about P. There are lots of other things that are very useful in papers. Right. So, but for those of you who want to know, and I'm not going to read this all out. You're very welcome to read these slides at your leisure. But these are the types of study that generally you're going to come across. So RCT, everyone knows, gold standard, and apparently Well, no, it is. I mean, if it's done of a properly properly conducted RCT, is very powerful evidence for a genuine effect. It's not foolproof. Those of you all not may remember a drug called activated protein C. First RCT was done brilliantly. It showed it had some effect, it had some benefit, and then a subsequent RCT showed no benefit. Was the drug magically less useful the second time around? No, I mean, it's because, for those who are interested, it's because people are better at treating sepsis. But it's, so the RCT doesn't necessarily guarantee a good outcome, but it is probably the most robust evidence you can have for an interventional study. And then you have things like cohort studies, case control studies, which to my mind are very, very similar. It's quite hard to work out the difference. But essentially, a case control study is always mostly retrospective, and it's where you look at two groups of patients who are matched in everything, but the thing you're looking for. So you match their age, you match for weight, you match for everything. So that's why the studies control, the two groups have similar characteristics, but it's not prospectively done, it's retrospectively done. Whereas cohort studies really they're both observational, but cohort studies are very much observational. And it's what we tend to do a lot in RCU. You follow groups, or you look back in groups, or look at groups of disease, groups of patients, and have a look and see what happened to them. And the biggest sort of cohort study was a smoking and lung cancer. I hadn't realised that it was done in doctors. So one of the big cohort studies was looking at a load of doctors and then looking at the ones who smoked and the ones who didn't smoke. And the ones who smoked died of lung cancer. And the ones who didn't smoke had a lower tendency to die from lung cancer. So, and then, the other types of studies you can see there. Qualitative studies, we don't do much about. We don't really learn about them in medicine. It's always seen a bit of the soft science. But qualitative work is increasingly used in looking at quality improvement, but looking at sort of the sort of softer outcomes of things like ICU. So looking at patients who've got PTSD and as an example, their experience of labour and anesthesia. So you may come across more qualitative studies, and if rigorously and robust, they are very useful. And we've all had systematic reviews, cynically described as taking someone else's research and making a paper out of it. But essentially, it's a study of studies. You take loads of studies, and you spend hours and hours doing various statistics to try and work out whether those studies together conclude a useful result. Okay. So, and now the statistics, and I'm hopefully I'm not going to labour this point too much. But anyway, so when you're reading the statistics section, most people skip over it. That's completely understandable, but it can be useful. And certainly, if you're in the position of reviewing papers for publication, you need to get your head around some of it. So we'll talk a bit about this in a minute, but you need to look at whether the test is appropriate. If the authors have come out with some random weird test that you have never heard of, and it's full of lots of obscure words, it kind of often suggests that this is not a very significant, there isn't much of a difference. Because you normally go for weird tests when you're doing what's called p-hacking, you're trying to find a p-value. But actually, sometimes there are weird tests you haven't heard of, which are novel and new. Sorry, I'm on call. So it doesn't really matter what people do as long as they justify it. So you need to make sure that when you're reading it, there's clear justification for why they've done what they've done, and actually that applies all the way through. And something that's increasingly important, and it comes in with some of the Bayesian, which we might have heard last time. If you heard the last talk, that's a bit about that. Is recognizing that the limitations of p-values, but also more important for clinical work, what you really want to see is the effect. So how strong an effect is the intervention? How strong an effect is the risk factor? And almost a better way of identifying whether that effect is useful and is relevant is looking at the confidence interval. And I'll give you an example. But just don't focus only on p-values. It's what people have done traditionally. Best avoided. Okay. So this is a fun game, buzzwords. So the idea is so the reason I've got this is basically sometimes if you don't really know the methodology, you can sometimes use the stats to work out vaguely what kind of methodology they're looking at, because people do use words that you've barely ever seen before, and actually it's used to describe things already happening. So those are the royal. Can you, this is like one of my 8-year-old's games, can you match the boxes in blue to the boxes in red? So what sort of statistic would go with something like this from an RCT? You're allowed to join in other hospitals if you want to, and your microphones are working. So RCT, what we're saying. So we've got one person saying sensitivity. Anyone else joining in this exciting game? It's not really difficult.
Harris got his hand up.
Who's got his hand up?
Gone. It's at the Glenfield.
Hello, Glenfield.
RCT.
Yeah.
Relative risk reduction.
So,
Okay.
so you asked the relative risk reduction.
Okay, good. Okay, well, we'll go through in a minute. Because I've realised, oh no, I have done it right. There we go. Oh, look at that. Magic. Check out my PowerPoint skills. Right, cohort studies. What does that go with? I'm not sure what it goes with. Oh yeah, no, I do. I remember that.
What
Oh,
cohort?
don't be shy. I'll only be sarcastic if you're wrong.
We're going cohort. We're going with logistic regression.
Well, Paris, you're on fire, man.
It's not me. It's the team. It's the team at Glenfield.
No, I appreciate it's definitely not you, Paris. I understand. Qualitative studies. Now, this is an easy one because if it's a word, if it's something you've never really heard of and makes almost no sense to you, then it's going to be qualitative.
What's the difference in content comparison?
We're going with content comparative.
Absolutely. So I've never heard of content comparative. I can sort of work it out, but diagnostics. Emily, you got this one earlier. Yeah, sensitivity for diagnostics. Systematic review. What do people always put in a systematic review? Forest plots, right? And that means survival must be Kaplan-Meier. Do people know what Kaplan-Meier graphs are? Vaguely. Yeah. Zoe and Matt have got it right there. It's waving your hands in the air. No, it's a change in survival over time. But we can talk about these exciting things in another talk if you want. Let me know in your comments below. Sorry, I'm not on YouTube, am I? Right, breaking down stats. So this is relates to my last talk. So if you've been asked to, or you're really interested and you want to look at the stats, then before you actually read the statistics section from the methods, you can say, what are the data? So what kind of data, what sort of information is being put before you? So this is before you get onto results. And the different types of information, so descriptive, kind of more qualitative data, but essentially you have continuous data like age, height, weight, ordinal data, so that's categorical data that has an order, so like EWS scores. So you can't have an EWS of 1.5, but 2 is worse than 1. And nominal data, so like, what's your favorite color? So there's no order to it. I mean, obviously blue is superior to all other colors, but most other things, if there's no order to it, that's nominal data. So this is very frequent in statistics that people talk about. And the next question is then, how are those data distributed, or how have they tried to convince you it's distributed? And essentially means, does it follow a Gaussian distribution or a parametric distribution, which will give you the mean, or so that's the bell-shaped curve, or is it non-parametric, which is the wonky bell-shaped curve, where you're looking at medians. And there are other distributions, and there are statistical tests based on those distributions, so you have binomial, but essentially most data that you'll see will fit into those categories. And the thing that becomes really important later on is which data, I mean, how they analyze the data points. So what groupings have they used? Have they actually compared groups properly? Have they taken a load of load of data points from the same samples and kept repeating statistics till they get to the right answer, or they actually corrected repeated measures. And what's null? So what is the null hypothesis for that particular statistical test they did? And I'll talk about that more in a minute. So then the sort of questions you'll be looking at when you're trying to drill down on statistics. But ultimately, we make assumptions when we read a paper that's been published. We make assumptions that the data have been already analysed properly because it's been peer reviewed. Unfortunately, peer reviewers are variable, and a lot also don't necessarily understand stats. I mean, I'm not particularly, I don't understand stats that well. So yes, it's the peer reviewers who should be looking at the stats and making sure they're rigorous and accurate. But you know, as we discovered with Andrew Wakefield and various other authors, sometimes the stats aren't valid. So this is what some people like to do. I don't, but some people like flowcharts. So this, please don't try reading these. I mean, if you download the thing later, you can have a look at them. But essentially what I'm trying to demonstrate is there are so many statistics and there are so many possibilities, there are so many charts, and there are so many different types of paper which have different stats. So trying to summarize, trying to work out the best statistic for the data you're reading is not easy. So you can do what I do, which is cheat a bit and is read about statistic they've used and see if it's applicable to the data they're presented. So I'm kind of doing it backwards. So there's some really, really good stats guides you can use. And again, download these and click on these later. But GraphPad is what I use a lot. I think statistics guide and that is really useful. And it gives loads of examples. So you don't need GraphPad to read the guide. So it is good. There's this handbook of biological statistics I've heard people recommend. For people who use SPSS, there's a statistical guide for that. I mean, the other thing, the paper will often say what software they use. So the other thing you do is if they say they use R or some other software, you can always go and read about the tests from that software and it'll tell you whether they did the right thing or not. Or you can JFGI, just use Google and see and put the test in and see what comes out. Often it comes out with a Wikipedia article with loads of maths in it, but there are often other things that break it down, Barney style, a bit more easily. Okie dokie. Right. So this bit's slightly heavy going, so I'm going to try and be relatively gentle with it. But there's this quite relatively interesting article by these authors up here, which again, if you download it, you can click on it. But it's about common statistical mistakes that that authors often make and reviewers don't notice. Most of the mistakes are around p-values because somehow we have come to take p-values as being vital, and which has led to a lot of people generating p-values that are either not relevant, not important, or just basically completely false. So what is a p-value? So we all learn that it's if you're p less than 0.05, you can be 95% certain that, or confident that your hypothesis is proved. That isn't really what a p-value is. So a p-value is the probability that the null hypothesis is correct, which is kind of the inverse of what I just said. But it's for the specific set of data you're testing. And ultimately, statistical tests are about statistical tests don't care what your data are. They don't care what the numbers represent. To a statistical test, it is just a bunch of numbers. It's a number of data points which you're comparing to another group of data points. And it's us as humans that translate that into what we think is right. And I think it's really important to remember that you can take any random set of data and run tests on it. And actually, if you run tests on it, 5% of the time, you'll get a p-value that reassures you. So it is literally just a set of numbers, and they are very precise tests for the numbers you're looking at. And there are lots of things you can make. You can make mistakes by inferring incorrectly, by forgetting what your data are actually describing. There are loads of hazards, and I think before anyone themselves goes on to do statistics for papers and things, they need to have a little think about what it is they're testing and how they're testing it. The other thing about p-values, as I said earlier, they don't tell you how strong an effect a drug or an intervention might have. The p-value just tells you, is the difference or the association between these groups of numbers, is it significant? Is there a 95% certainty that those groups are associated, or those groups are different? It doesn't tell you how big a difference there is. So I'm sure you've read papers where people say, this test, this test shows, this shows that these data are highly significant. Well, that doesn't really mean anything. It tells you the p-value is low, but actually, to get a different p-value is actually very easy. You just have to add a couple of numbers in or remove a couple of numbers, and you get wildly different p's. So the p-value doesn't tell you anything about the size or the strength of the effect. It just tells you how confident you are that there is a difference, not how big that difference is. Does that make sense? Okay. And the other thing is absence of significant is not absence of effect. So a number of things. So if you don't have many recruits, you don't have many data points in your samples, then you may not see a significant difference between the groups, although you may see an effect size, but so you may see there's a lot, you may look at it and see a graph and say, look, there's a large difference, but you haven't got enough numbers to say there is a significant difference. And that's what essentially an underpowered study would do. Likewise, and this comes to point 5, I think, you might see a significant difference, but the effect size is small. So the classic one for that is pain scores. I remember a number of times I saw papers about pain scoring, and they say, right, our intervention of talk to patients loads and loads and loads, drop their average pain score from a pain score of 7 to 6.6, p less than 0.001. And so you go, okay, well, that, yes, it's significant. You had enough samples in that group, enough samples in that group that you got significant difference. But who cares? Dropping your pain score from 7 to 6.6, that is not a big effect. And it's almost entirely explainable by error, by sampling, by patients' error within the measurements. So this is why the p-value has a role, but isn't as significant as we think it is. Something else I can say about that. Right. Yeah. So I said this effect size is more meaningful than p. So as I said, it's really, that is actually what's more relevant to us as human beings rather than groups and numbers. The other thing you'll see is that people will. This is okay. So people will write in their paper, this was a highly significant result because the p was less than 0.001. And this is amazing. This has proven that our drug cures cancer in our 6 patients. So overrepresentation of significant data, the mistake is assuming that the value of p is how important and how strong and how relevant your data is. Nothing of the sort. Absolutely nothing of the sort. As I keep going on about, it tells you that that data point is different to that group of data are different to that group of data. It does nothing else. And any paper that tends to lots of papers do it, they overrepresent, they say how important their information is. And it's very easy to say, actually, it's not. So just be wary of papers that go on about how amazing their information is. The other important bit is that the p-value you generate depends on the number of assumptions you're making about the data you've got. And so if you've got sampling errors, so you sampled from different populations, and for whatever reason, it's a cluster effect, you end up with more overrepresentation of a certain group within that group, you can end up with averages that are not representative of what's true for the rest of the population. Or you may also describe the data incorrectly. So something that's normally has a parametric distribution in real world, in your data set may have a non-parametric distribution, and vice versa. So the distribution of the data and the characteristics of the data also determine what test you do. So again, if you say in your study how amazing our data is, this demonstrates this and absolute proof, it can't be unless you tested every single person in the entire world. The classic correlation and causation, 100% of people who drink water die. I mean, so the classic correlation and causation argument, because things are associated, doesn't mean they're causal. And there are loads of examples of this. I think that's someone I read the other day. I think it's motor death and the amount, I don't know, there are loads of them. Car seats and babies rear-facing car seats and things. There's lots and lots and lots and lots of papers where people have said, there is this association, this needs further investigation, or there is an association, this means blah, blah, blah. But, I like the water and death. The more water you drink over your lifetime, the more likely you are to die. Right, so everyone stop drinking water. Right, and the final point is small samples. Now, small samples, they can provide useful data. You just have to be careful when you see papers which are small samples. And essentially, most small sample papers either are because you're looking at a really rare disease, for example. You might have, only 1 in a trillion people have this disease, so you only get 3 or 4 people to look at. So sometimes there's no choice. Other times you're doing this pilot, you're doing to generate hypotheses, to generate more studies, and that's absolutely fine. You just have to be careful. First of all, as I've talked about already, the actual distribution of the data may be different. There's this phenomenon called p-hacking, which describes lots of ways of trying to get the right p-values. But one of the common ways is, right, I take 10 data sets, I run my statistical test, and I get a p of 0.07. Oh, damn it. Right, let's add more data in. Yes, no, now it's gone to 0.06. Right, add more data. Yeah, I've got a p-value of 0.05. Hooray. The problem with doing that is that you can keep adding data and adding data and adding data and adding data, and at some point you'll always get a p, well, 5% of the time you'll get a p-value less than 0.05. Just by adding more and more information. And you can test this. You can run Excel programs and Excel spreadsheets to demonstrate this. If you just keep adding information, every time you do a test, you're more, you increase the chance that you're going to get a p-value that you want. So this is why it's really important when you're reading papers. I mean, if you're going to be really, if you're going to be a reviewer, what you should do is go back and look at the original outline of the project and make sure they're stuck to what they said. And if they haven't, and also stuck to their recruitment numbers, and if they haven't done that, you need to see in the paper there's justification for not doing that. But it's the danger of stopping studies too early, which we know happens, and the danger of, it's the danger of stopping too early, either because the p-value is too low, too high or too low. So usually they'll say, oh, right, we've reached a p of less than 0.5, let's stop the study. But actually, if you carried on the study, you may well show, just as the time and the distribution and the numbers of data points you get, actually the true p-value, the true difference was insignificant. So small samples, and it's partly also a reason why, so this kind of leads on to the other thing. If you've got small studies, to show a significant difference, to avoid an alpha error, you need a big effect. And the example I use is pushing people off cliffs. That's not something I do regularly, but if you were to do a study where you push people off cliffs and see how many died, you wouldn't need to do many to demonstrate that it's not very good for you. So that's a very large effect. Standing on the edge of a cliff, being alive, falling onto the bottom of the cliff, being dead, that's a very, very large effect. So you don't need men to do that. But if you did that 1,000 times, yes, you'd be psychotic, but also you would find that some people do survive. And what this kind of demonstrates is that if you have a small study with a large effect, you tend to overestimate the true effect size. So you would say, pushing me off a cliff, 100% of people die. If you do it 1,000 times, it may actually be 97% of people die. And it's a slightly ridiculous example, but it's there to illustrate a point that small samples tend to give bigger effects. And you see this in the literature. You'll see, we did the study, it demonstrated X, Y, Z, cured, made everyone in ICU live forever. When we did it as a big study, there was no effect, there was no difference. And you see this time and time again. Small studies showing an interesting question, suggesting a really fantastic treatment, and then the big study shows no difference. And sorry, if you go to these links, you'll see loads of other things I don't quite understand, but a few things which are, about the mistakes. But I think these are the important ones, and they're all basically based around P, right? So this is what my dog does when I try and tell her to get off my lap. So the discussion, so what? So this is the so what question. What is the point in this paper? And this is where the authors, I think, should what I call humanize results. So to put the results into context, explain the results in a way that a normal person can understand. Explain why they're relevant, explain why their study's okay, what else they could do better next time, what the other studies and literature say and why the study's different or the same, and to justify the conclusions. And by that I mean not say how amazing they are. It's about actually justifying what they found, being rigorous about that and future work. And these are things you do. So when you write, if you write papers or when you get to write papers, this is the kind of content you want in your discussion. Okay. So this is, so hopefully by the end of that, you should be able to say, okay, so what? Okay, that is actually quite interesting. That's quite useful. Prone to, perceive the study, putting people prone. Well, that's turned out to be really very useful with COVID. And the final bit is, are the results relevant to you as a clinician? And there are a few things you can ask. Is the population they studied the same as the population you see? So Placebo, for example, was a lot of franchise people in monotonium, which were used to putting people prone. In the UK, most of our units were not used to or regularly putting people prone. So a very justifiable argument, putting people prone is riskier in a UK setting. Fortunately, we've all become really rather good at putting people prone. Well, so unfortunately, we've had to do a lot of it recently. And it links to the intervention being feasible. So yes, we see a study, it says prone position fantastic, but is it feasible to train everyone to do that? Are we going to do enough proning, putting people prone, to make it worthwhile training everyone? And this thing I find really interesting is the risks and benefits. So what we often do, what often papers do, they're not powered to detect significant risks. They're usually powered to detect benefit. So for example, let's say it was demonstrated that putting an intracranial bolt in someone's head and measuring ICP improved outcomes in sepsis. So, and you recruited on it. Well, I've got a thing there, 3,000 patients for that. The study will not detect, let's say you recruit 1,000 patients, The study will not detect a risk of 1 in 1,000 unless you have 3,000 patients. So you need another 2,000 patients to detect risk of harm. I'll explain it a bit more clearly. But always remember, a lot of studies aren't powered to detect harm. And there's a thing in the rule of 3, which really mainly works for parametric data, but essentially, you can read it both ways. So one way of reading it is a 95% confidence to detect an adverse event is 3 divided by the number of the trial. So 3,000 patients receive the drug. Divide that by 3 divided by 3,000 is 1,000. And you can say therefore there's a 1 in 1,000. So you should have detected a complication in that trial with a risk of 1 in 1,000. So 0.001% or 0.01%. Likewise, you had 300 patients in a trial. 3 divided by 300. 3 divided by 300 is 100. So 1 in 100. Yeah. So you could detect 95% confident you detect a risk of up to 1 in 100, but anything more than that you wouldn't detect. And it all depends what the risk is. So if an integrated vault, the risk of meningitis, that's quite a bad thing to get. Whereas the risk is of a slightly broken nail, maybe less significant. So that's what you as a reader have to work out. But it is quite useful to remember this rule of 3, just to think, well, actually, the risks, these risks haven't been looked at, and that this could be the rate. Cool. Okay, I think we're near the end. Don't panic. Right. References, no one ever reads the references, but actually there's a lot of information in there if you're interested in the paper. So you read the paper and it's really interesting, it's really grabbed your attention. The references often have all the background stuff leading to this paper and the comparatives, but also it's really interesting, they often see the methods. So they often tell you how other authors have done it. And so if you're planning a study or you're writing a thesis and you need to work out how people do things, references is where the methods are. But I've come across this when I review papers. Sometimes the references are completely wrong or made up or are just completely irrelevant. They just put something in that's got absolutely nothing to do with the papers being published. I did once edit a Wikipedia article because they made a reference that was wrong, which I realised was very geeky and sad, but it was when I was doing my thesis, so you have to forgive me. Right. So my final secret to reading a paper: get someone else to do the work for you. So if you're asked to prepare a journal, a journal club, usually it's a big paper, loads of people have written stuff about it. So actually ignore everything I just said. All you have to do is read other people's comments and present that as your own. You look amazing. Right? But seriously, the big journals, especially when you're time pressed, other people have done all this work for you. And it does help you. It's not just, well, it's cheating. No, it's not cheating. Just looking at the answers before you finish the question. That's my secret. That's how I've got so far in my career. Right. That's enough from me because I'm just rabbiting on. So this is my dog being useful and useful links. So if you are asked to, if you want to do it properly, this link here is really good. Again, I'm sure you can download this PowerPoint presentation. This basically has pro formas to fill in. So there's an RCT, there's a critical appraisal tool for an RCT, and you just tick the boxes and it explains what relative risk ratio is, relative risk reduction, things like that are. And there's another one which is more generic, which is a bit harder to understand, which you can go to as well. Right, that's enough for me. In future, my next plan is to talk about how to do research, and I guarantee some more pictures of my dog. Or alternatively, just in your feedback, tell me what you want for me to talk about next time. Not for me to shut up, you're not allowed to write that. But no, you can just whatever topics or anything statistics, research related, I'm happy to talk about mostly. Right, I'm losing my voice. Any questions from anyone at any other hospital or this one here? Any comments, concerns about my mental health? Paras, you got anything to say for yourself?
First of all, thank you. That was really good talk, actually. Really useful. Certainly, I fall into the category of having to read journals for this project of doing journal club. So I'll try and read more journals for other reasons in the future. No comments really. As I said, really useful, particularly about the p-values. I found that particularly interesting. I guess most papers very heavily concentrate on the p-values and talk about the statistical significance. So yeah, it's a bit of an eye-opener in that aspect.
I think things will change. There's a real move against p-values now. Okay. Oh? No, I mean there's a real move kind of against them because it's led to a lot of publication bias. Because basically people only publish things with significant values, and it leads to a lot of trials basically being shoehorned into fitting a statistical test, not the other way around. And then there is recognition of publication bias, so you only ever see positive results. And the problem is the positive results aren't positive because they're based on incorrect interpretation of p-values. So hopefully in the future we will move away from them, or at least, I mean, they have a role, they have a really important role, but it's about using them correctly, and that's actually not straightforward. And I think if you don't use things all the time, you kind of forget how to do it as well. So there's statistical tests I use more than others. So sometimes I'm using one a lot, and I'll get to know about it, and then 3 weeks later I'll forget all about it. And it's the same with reading, which is why you're supposed to carry on reading all the time. Okay.
The other thing I was going to mention is that you mentioned methodology of papers, and I have a tendency personally when I'm flicking through journals to only really focus on RCTs or meta-analyses as the most important sort of papers to read. As again, it's just more of a comment more than a question really, but I think there's a sort of a shunning away of using other methodologies because they're not as, I don't know, they don't make as much of a, or have as much of an impact as. Do you agree with that, or do you think that other methodologies still have a significant impact in research?
Yeah, I mean, it's a big conversation at the moment. The problem is that for rare diseases or small specialties, RCTs don't work because you can't recruit the numbers, you can't power the studies enough. And for the other area doesn't really work is ICU, where you actually don't know what disease they're treating. So one of the main reasons sepsis RCTs nearly all the studies into treatments of sepsis come out with a non-significant result, whatever that means, and they have quite small effect sizes. And the reason is because we don't know what sepsis is. I could rant about this for ages. But there's no diagnosis of sepsis. It's not a diagnosis, and we don't know when in the phase of sepsis people are in. So RCTs, if you have clear groups, if you have a clear diagnostic criteria, and if it is a very rigorous way of doing science, but it just doesn't work for the real life messiness of human beings and their disease presentations. So it just means that there are other ways of studying it which raise questions and are important and suggest evidence. You just have to accept there are limitations to the information you're using. And one of the other, I didn't put it up in one of the mistakes people make statistics, is the search for certainty. Statistics don't give you the answer. Papers don't give you the answer. They don't tell you the truth. They just tell you a confidence and how confident you are in a certain belief or a certain theory. And smaller papers or non-RCT papers can help you just, they contribute to the weight of evidence to suggest something is true or not. But it's partly why medicine takes ages. Anything it takes ages to change. So yeah, I mean, RCTs are, if you're able to follow the rigorous process of an RCT, then yes, they are powerful. But in certain specialties like intensive care and to an extent anesthesia, the demands are too great. And we have to accept things like cohort studies and case control studies, and to give us the information we need to suggest that we may make a difference. And the idea is you repeat those studies in different groups, different cohorts, and then it builds up a body of evidence. Most of the council work wouldn't exist if it was relying on their RCTs. They use something called adaptive trial design, which is something else we can talk about another time. Okay.
That's great. Any other questions from anyone?
Either. Okay.
Lovely. So I think so next week we've got one of the renal, I think it's one of the renal registrars talking about hyponatremia, so Dr. George De Silva, and the journal club for next week is Dr. Hussain, who's going to talk about the ideal ICU trial, I believe. No journal club this week because it was missed, unfortunately, so we're going to reschedule that for the following week, most likely. Cool. See you guys later.
Thanks, Simon.
Okay. All right. Cheers. Thanks very much, everyone. Thank you. Bye.